Good morning, Phreaknic. My name is Michael Snyder, and I'm here to give the 10 o'clock talk. My talk is about magnetic rainbows, and uh, I have an undergrad degree from Murray State University in physics. I also am a PhD student at the University of Louisville. Okay, the first part of my talk is Snyder's security protocol. And this is just a little protocol that I came up with. I think it will increase encryption, and it's at layer 4, so we can use everything we already have. We can just add another one to it. Okay, why do we need a new security protocol? Well, basically, computers have gotten more powerful, which means the more powerful the computers get, the less secure or old encryption is. It's basically Moore's law. And there's some possible strategies that we're not using now that we could use. And basically, I just want to go over the strategies. Now, the most common encryption is based on factoring large numbers. And, we see this a lot in public key encryptions. Now, there's nothing wrong with factoring large numbers. What I'm pointing out is there's many other ways of doing this. We're just solving one mathematical problem. There's a whole list of mathematical problems we could be solving instead of just factoring large numbers. So to me, the factoring large numbers is just the low-hanging fruit. There's many other choices. Next slide. Now, the present encryption is like the Great Wall of China. It's very tall, and it's very long, and it's very secure, as long as you don't happen to guess the large number that was being factored. Some things to notice. Notice that if the wall is broken at any point, if the security is penetrated at any point, then it doesn't do any good. And I think the Chinese found that out a few thousand years ago. It's a great idea, and it does work, but it has some significant downsides. Now, when things go wrong, they go really wrong with the present technology. The present encryption technology. Next slide. Now, we already know possible solutions to this. Now, with the present technology, if you break it, then you get keys to the kingdom. There's no second chance. We're putting all of our chicks in one basket, or all of our eggs into one basket. Now, there's another way of doing this, and we know from evolution that diversity is the solution to adversity. And basically what that says is, when things are going wrong, you want to try every possible solution. And that's exactly what evolution does. It tries every possible solution. That's why I'm standing here right now. I'm one of the possible solutions it came up with. Okay, Snyder's security protocol is a application layer 4 XOR encoding, and I'm assuming a connection full TCP, which basically means I don't want to deal with missing packets. We'll let the lower level protocols take care of that. And the way I'm envisioning this, it would be transparent to all the low level encryption. You could run your regular VPN at one level, run your SSH at another level, and this would be on top of those two, and basically just be another layer of encoding. Next slide, please. Now, the visual image I want to use for my encryption is, instead of a big wall, that has places, where everybody knows where the weakness is, I'm using a infinite series of speed bumps. where each speed bump, the encryption's not that strong, but it's independent from the next speed bump, which is independent from the next speed bump. In other words, if you hack into speed bump 1, that doesn't give you the keys to speed bump 2. You still have to do that work. So on the regular encryption, if you break into the castle, you get everything inside the castle. With my encryption, you break past the speed bump, there's another one waiting for you. Now you might get a few packets, but you're not getting the whole data stream, which is the goal. Next slide, please. So the status quo encryption makes a super duper key and hides it. Never ever puts it on the wire. My security protocol says, screw it. Make a whole lot of keys and use each key one time. One-use keys. And if somebody guesses one, if somebody gets one of them, that's okay. My data stream might be 10,000 packets long, and if somebody guesses a key and gets 5 packets, I'm not worried about it. Next slide, please. So instead of a big wall that nobody can get through, and they also happen to know where all the weaknesses are, we have a if-net series of small roadblocks, small speed bumps. And just because you break into one part of it doesn't mean you get another part of it. They're all independent tests or levels of a video game, if you want to think of it that way. Next slide, please. Okay, so this is my basic code, and what I did was I just took my ideas and I wrote them down in C++ format. The code, I won't go line by line, but I will tell you in general what it's doing. Basically, I'm starting on the server side with a hexadecimal key, and I'm using it as an XOR key, which XOR, you can take A, XOR it with B, and it produces a value. If you take that value and XOR it with A, it'll get B back. Basically, you can't lose any information by using an XOR key. So I'm taking an XOR key, and I'm just permutating it. I'm just taking a mask and changing it. And the client computer, we'll go to the next slide, and this is more of the server side. We'll go to the client side, which is the next slide. On the client side, the client watches for this permutation to happen. And so the server's talking to the client, and they both are in sync. And then randomly the server changes the key. And then the client has to try all the possibilities to find the key. This is very similar to having a conversation with somebody and they change the subject. And then you have to use all that mental processing power to find the subject they're talking about. So this is the same idea. The server's talking to the client. The server changes the key, and the client notices, and then the client has to find the new key. Now, once the client finds the new key, it does something very special. It generates a whole set of security key parameters and hands them and encodes the new key. Now, remember, the new key has never been on the wire. The server knows the new key. The client found the new key. So the server changed it. The client found it. It uses the new key, makes up a whole new set of security parameters, including another XOR key, and transmits it to the server immediately. So we have, server changed the key, client found it, client made a new key, client transfers it to the server. We have a lot of good things going on here. The first thing being that the server has used very little CPU power. Now, using XOR keys and changing an XOR key is minimal CPU power. The client has used quite a bit of CPU power, and we want that to happen. Let me explain why. Imagine you're an eavesdropper, and you're trying to figure out what this conversation's going on. Now, if you can just listen to the client side and the server side, and the server side takes one CPU unit and the client side takes one CPU unit, then the eavesdropper only has to spend 2 CPU units to decode it in real time. But we don't want the eavesdropper to decode it in real time. So if the server side uses 1 CPU unit and the client side uses 7 CPU units, then that's a whole different ballgame, because then the eavesdropper has to use 8 CPU units to listen to it in real time, which means if he's listening to thousands of conversations, he has to pick and choose which conversation he wants to listen to. Okay, so basically, your iPhone and your other devices, even at their slowest CPU speeds, still have surplus CPU power. So by putting some encryption load on the client side and not on the server side, we help ourselves in many ways. Next slide. Now, just using my security protocol as it is written in those 4 pages, I think would be, a big, a significant change for the better. But there's a lot of other things we can do that we're not necessarily doing now. So this slide is called extras, and then we'll look at the other things we could do. Okay, so my idea, one of the extras we can do is standardized non-standardization. And what that means is basically we don't want to do everything the same. We don't want to do it the same way other people are doing it. If they're using a 56-bit key, we want to use a 64-bit key. Or if they're using, message digest, MD5, we want to use SHA. We want to do things differently all the time for more security. And one way of doing that, especially, in my protocol, I need to pick a new XOR key because I don't use them very long, is just coming up with a bunch of different functions that produces integers. Next slide, please. For example, if we just take the integer function of the timestamp, we would just, we would get the timestamp in seconds, and that's a big long number, and we could use that as XOR key. Now, of course, using the timestamp as a XOR key has a downside that the eavesdropper may try that and figure out what you're doing. But there's other choices. What if I take a random number between 0 and 1, multiply it by 1,000, and add it to the timestamp, and just take the integer value of that value? So that's a known number plus a random number, which would be pretty hard to figure out. But there's other choices. For example, let's take the sign of the timestamp and add it to a random number between 0 and 1,000, and take the integer value of that. So the sign of the timestamp is very interesting because it cycles over and over again, and of course the random number is random, so that's a pretty good way of producing a random key. But there's other choices. For example, let's take the timestamp in seconds and take the square root of it, which will produce another number, divide it by 5, and add 4.5 to it, and then take the integer sequence of that. Now, can we do that? Yes. Could the eavesdropper figure out, how you're generating that XOR key? Maybe they could, but that's no big deal, because, there's another way of doing it. Maybe I'll take the timestamp and raise it to a random number between 0 and 1. Now, that will also produce a random number. Now, I'm not suggesting that we use any one of these ideas. What I'm suggesting is having a big, long library list of all these possible functions, including user libraries, including user entries. And then the computer randomly picks one every time it generates a key. Now, remember, the server has no preference on what keys gets passed to it. It'll use any parameters that's passed to it. Next slide, please. Okay, in this slide, we have a bunch of a bunch of duct decoys. And basically, the idea I'm trying to express is in my code on the client side, the server is using a key, and then the server changes the key, and the client notices, and then the client searches through all the possibilities, and the client knows all the possibilities because previously it had passed those possibilities to the server. Okay, so imagine the client searches through all the possible permutations and doesn't find the answer. Now, what does the client do? Well, one possibility is just for him to drop the packet like it never received it. And that's a really nasty thing to do to the eavesdropper. So the eavesdropper really doesn't know the permutation window. It doesn't know how big a set of permutations to check. And if you make a packet that does not meet the requirement that it's encoded with a MD5 value, if you make a packet that has the wrong MD5 value for every possibility, then the client will just kick it out. It'll try the limited sets of limited choices, and after every choice is tried, it'll kick it out. But the eavesdropper won't know that, so the eavesdropper keeps trying more and more and more XOR keys. This is a pretty nasty thing to do to the eavesdropper. Next slide, please. Another possibility is what if you open a few tunnels instead of one encrypted tunnel? Maybe have 3 or 4 encrypted tunnels, and then this using round robin pass the data to different encrypted tunnels at different times. As long as the client knows what tunnel to look for how to resequence the data, there's no problem. We could do this very easily. Now, imagine you're an eavesdropper, and you want to hear the whole conversation. Well, if you just focus on any one tunnel, you don't get the whole conversation. So this is meant to be a logistic nightmare. And you could do the same thing with a single tunnel by reordering the packets. If it's bulk data and you don't care, and the client knows how to resequence the packets, then you can mess up the sequence on the one hand on the server side and reorder a sequence on the client side, with the downside being latency. But a lot of data protocols don't care about latency, but some do. Next slide, please. Okay, so basically now we're looking at an infinite set of speed bumps. And each speed bump, the client makes up the communication parameters and passes them to the server. And the server will do whatever the client passes. It will use this whatever key, whatever permutation window, and so forth. So that brings up the question: can we increase our security by using this independence? Most of the time you don't have this freedom to completely change a key, and that's what this next slide is about. Next slide, please. So, can we change key sizes on the fly? For example, can the first speed bump be 64 bits XOR key, and can the next one be 128 bits XOR key? And could we change back and forth? And the answer is yes. My security protocol doesn't care. The server will, when it gets its instructions from the client, it will use any XOR key it's given, and it will use any permutation mask that's given. It's basically, it's a computer. It'll follow the instructions that's given it, which means we can change key sizes on the fly. Which, could you imagine how frustrating that would be on somebody who's trying to decode your packets? On one's, not only did we change the key, but we changed the key size, from one packet to the next. Another possibility is, can we use odd size keys? Have you ever heard of using 73 bits or 52 bits? Well, 52 would be an even number, but even 53 bits. Now, can we use odd sized keys? And the answer is yes. Now, the code gets a little ugly because you have to use bit operators instead of byte operators. But if we imagine a data stream as a sequence of bits instead of a sequence of bytes, then we can use 127 bits as a key, which would completely mess up your byte boundaries. But assuming the client knows how to reconstruct the byte boundaries, it's not a big deal. So, in other words, could you imagine being an eavesdropper and somebody's using 73 bits instead of 74 or an even number? That would make it very hard to decode. Oh, what's the maximum size key we can use? Well, if we know the size of the packet already, and let's assume that we're using 1500 byte packets, then the maximum key size that the client can transmit to the server is, surprisingly, 1500 bytes. We can use very large keys. There's really, the packets size and the key size are basically, the maximum key size is the packet size. Next slide, please. Now, all this effort, why should we make all this effort to prevent an eavesdropper from listening to our work or data? And the answer is that there's many eavesdroppers out there, and information is power. So imagine that you love your government and you want to share all your data with your government, and I have no problem with that. But it's not just your government listening on the internet. There's China, there's India, there's economic reasons to listen for data. There's military reasons to listen for data. It comes back that information is power, and power corrupts. There's really no way around that. Imagine if you were a person who could have all the world's information at your fingertips. Would you use that information correctly? I probably would not. So, in a long story short, you can always make the case that it is disloyal to allow other governments to eavesdrop on your conversation. If you love the USA, it is disloyal to let China listen to my conversations, and vice versa. Next slide, please. Okay, so this is one of those memes from the internet. It says, "A nation of sheep will beget a government of wolves." And the only change I would make is put S on the governments. So a nation of sheep will beget many governments of wolves. We really need to protect our data just to stop the temptation of other people to see our data. Okay, next slide, please. This is the summary page for part 1. And basically, in my summary, we're saying that not all encryption has to be built on factoring large numbers. There's many other ways of doing things than factoring large numbers. My security protocol is based on the time it takes to solve the following problem. I have a data segment. I have an MD5 value, which is a message digest value, which is calculated from the data segment, and then I encapsulate both with a unknown XOR key, and then the client has to find that XOR key, and by finding that key, then it gives it a moment of security where it can transmit a new key to the server, and then the process repeats. So this is just a different kind of math problem. I have a data segment, I have a message digest value, and I have both of them wrapped up with a key. Now you could think of this, if you squint your eyes just right, you can think of the MD5 value as an eigenvalue. You can think of the key, the unknown key, as a eigenvector, and you can think of the data segment as a data matrix. So in this, basically I took some ideas from quantum mechanics and just applied them to this basic encryption problem. Next slide, please. Okay, that's the end of part 1, and I don't have enough time to start part 2, so we'll have to save that for next year. So here's the last slide. And basically, if you have any questions, you can email me at msnyder, that's MSNYDER, at revolution-labs.com. And if you liked my presentation, please send a few dollars my way. And that's the GoFundMe site, and my URL is ZA86D8WG. And I want to thank you for being my audience, and I look forward to seeing you next year. Thank you.